Thank you. Thank you, everybody. Yeah, so it's a pleasure for me to come back to biocomputing, bioinformatics, because when I started bioinformatics, the word didn't exist. So 1992, when we made the assembly of the yeast genome, and when we are sequencing by hand, I don't know if you remember, so when you were 100 pair of bars on your radio, you were very, very happy, okay? And so, and it took, yeah, to have 1,000 pair of bars, you were working something like 1 week. So when we did that, the bioinformatics was just not existing. And then it ramped up very, very fast. In 1995 at IGBMC, we made the first, I think one of the first software as a service system, which was a cloud. I mean, you log into a web interface, you copy paste your sequence, and the sequence were going to blast, but blast output was so crap. Then we go in a tool that perhaps still exists, which is what's called ballast, and ballast was just purging the blast output from all the duplicates sequencing, so that you can then have a list of unique sequences, and then we pile those unique sequences into cluster W, and then you open your protein alignment in cluster X on your computer. So this was a software as a service. This was a workflow, and we never call it a cloud. Never know why. We should have learned from the story. Anyway, so today what I want to show you is where the professional industry is moving. Not to sell you anything. I don't have anything to sell today. Just to give you ideas. Yeah, sales is access. So if you want to buy something, it's there. The thing is that I will show you our stack, our systems, and what we are doing with it, just to give you ideas. Okay, just for you to check what you are perhaps missing a piece of your hardware or of your stack, or perhaps use another tool to get it faster and get it easier to your solution. So the first thing, that is the HPE point of view on the future of computing, and that is now enforced by the CE regulation, by the way, on your side, is that the data is the center of what you have to think about. Because as soon as you are going to a human genome or something linked to a human disease or any human personal data, then the data should not move anymore, because you are responsible as a data producer to be able to remove that data from the internet if the human is asking for it. So you can't distribute personal data over the world like we did for the past 20 years. It's not allowed anymore. And also, we are thinking that we are misusing the network today. We are using the network, roughly 80% in the industry, to transfer data, while we should just transfer the results of the computation made near the data. We can discuss that, but this is the vision of HPE. We do not move the data, we make a data lake. We call a data lake or a data, a data lake or a data silo. And this data lake is connected to computes, whatever type of computes, to do whatever type of analysis you want to do. So the producer of the data is the provider of the way to analyze the data and is responsible of the pseudonymization of the data. So, come on. Do not move the data and then give access to the data to the users who need it. So, Monsieur Christ, please have a seat. So, the second thing that we learn from our experience in trying to help the industry to make clouds, so HPE is behind many of the known clouds, Azure, I will show you, as Advania, and many other clouds. Some of them I can't even cite, especially in the intelligent services area, we learned that there are many links between HPC and cloud, meaning that you can do HPC without cloud, but it's very hard to make a really reliable big cloud system without an HPC background. You need, so those are the difference between the two, but more or less, you always need a scheduler, you always need fast access to the data, and you always need to have something reliable at the end. So this is a typical cloud we make, and we call it for HPC because today everything is HPC. I don't know why. Even if you are using one node with 2 cores on a GPU, it's an HPC system. HPC was at the beginning parallelized, and today HPC is something that is faster than a laptop. That's the case. So to make a full cloud, you need an orchestrator, you need a cloud management platform, you need things to make the bidding. And there is one of the problems of the industry cloud. A cloud for the industry is not a contract between two entities. It's a contract, by the way, between 3 entities. We have the cloud provider, we have the user, and we have the procurement. So today, the main caveat or the main challenge of the professional cloud is to have the user able to use the capacities that the procurement forecasted. So that means that the procurement or the company administrators, who are the technical end of the procurement, should be able to control what the user is doing on the cloud. And the cloud provider should be able to optimize its infrastructure, so the scheduling and the number of nodes, bare metal nodes they are running, and the size of the storage and the size of the network to face the burst from the user. And the burst of the user should not kill the procurement forecast. And I can tell you a story. Okay, now I have to pseudonymize this story. There is a big company in Europe doing planes, and they are currently evaluating Amazon Web Services. And they face 2 issues today. First of all, they have 19 petabytes. They made a proof of concept on one of their services. And this proof of concept, they transferred 19 petabytes of data to the cloud. Today, they have no way to get it back home. Okay, so they are prisoners of the cloud provider. And this cloud provider also wants, they now want to make a contract like they did with us and with our competitors, which is a fixed price contract. But the cloud provider is unable, this cloud provider can't make a fixed price contract. Why? Because they are invoicing the data based on the IOs, not on the storage, but on the IOs. So imagine that you take a plane, okay, you have a model. So let's say you have a wing of A320. This wing, now you want to make a sharklet on it. So you know what is the cost of the modelization of this wing on the cloud. And then you add a sharklet. Adding the sharklet, increasing the grid, the mesh you are using for example, Fluent or ELSA, you increase the mesh. Then the mesh gets out of the, you increase the size of the physical memory you use on your compute nodes. This means that on the Linux system, you have less room for the buffer. Then you make more I/O. And a wing without sharklet, or a wing with sharklet, is 2 times more expensive on this cloud provider than the wings without sharklet. And you can't forecast this price. There is no way. So in the tools we are providing with our cloud providers, there is also a bidding part that is very important so that people can forecast the price. And in our multi-tenant systems, so multi-tenant is you have abonnement on many different clouds. And when you submit to your portal, your workload will go, where is your data? Or where is the less expensive cloud at that time? So that's a tool that we use for the industry. That is a multi-tenant cloud orchestrator that can choose on which cloud we are deploying to have the best price. And for that, the price has to be predictable. And our procurement, even in the public sector, the procurement do not like unpredictable expense. You have a budget for the year, and it's fixed. Or you have a budget for the month or whatever, but it's fixed. And you can't burst it. You can burst your HPC, but you can't burst the budget. So, typical things are the nodes you need for, and you know that it's an industry state point. There is no difference between the user and the administrator, but there you have tools for the users. This one, and this one is for user, but the scheduler, deployment, and monitoring for the administrator. What else? So underlying that, you have a compute, storage, and network, of course. And you try, if you want to make a good cloud, you have to break the silos. So if you are, I know you're more on the software part, but still bear in mind that you have to break the silos. Do not let the network guys doing things without talking to the compute guys and so on. It will never work. So that's what's already said by someone yesterday. So I move away. Not on Wednesday by the guy from EMBL. The typical reason to move workload to the cloud, it's easy. One thing that is always missing in this slide, and also in this one, here there is a line missing, is high energy density. And with the new CPUs that are arriving on the market, so the new Skylake, which is generally available next month, the SKUs can be up to 200 watts per socket. The new AMD EPYC was disclosed last week, is 180 watts per socket. You have to imagine that in 1980, we were at 4 watts per socket. And if you draw the watt per socket up to the Nightmare is a new many-core from Intel that will be out in 2 years. So you draw a logarithm, it makes a line with 22% increase per year, every year, starting 1980 up to 2020. There is no reason we can't go further. Every year, someone says, yeah, we are at the maximum. Well, I heard that with a 95 watt per socket, then 105 watt per socket. Now we are 200 watt per socket. We still can increase the density of the CPU. Okay? So that density is really a nightmare for the data centers. And what is killing the prices of many HPC systems or cloud systems today is the cooling. So bear in mind that with a bad cooling, you can increase the price, the running price, or even the CapEx or OpEx price of your system by 20, 30, up to 50%. Okay. So, I'm missing one slide, sorry. It was an ecosystem. Anyway, one of the partners we are working on, so today, as you noticed, probably HP had a big restructuration. So we get rid of the laptop and desktop system and printers that went to HP Inc. The services is going to CSC, creating a new company called DXC. So all the what we call management services, ITO, I don't know which name you gave it to. There are an application services. They are now in another company. Software guys, especially the guys who were developing OpenStack, were going to Micro Focus. And Micro Focus, you probably know because they are the owner of SUSE. Okay? And so HPE has to rebuild the ecosystem. And mainly because HPE is not is less and less the front provider of the solution to the user. Whatever is the solution, we are now using partners. Okay? So one of our partners in the cloud industry is Advania. Why Advania? Well, it's very nice because it's in Iceland. So it's quite a big company. They have many data centers. They have a lot of compute nodes. They have one of the biggest cloud in Europe, and they are targeting only the industry. They are not really giving services to end users like Amazon can do or Azure can do. They are very nice, mainly because they are doing free cooling in Iceland and in over Northern Europe. So they are all in free cooling. And in Iceland, there is another thing. We'll come back to, can you predict the cost of your run? It's because the electricity price in Iceland is stable. It's flat for the next 20 years. You know that you will not get more than 50 euro per megawatt hour in the next 20 years. So it's a very stable investment. In Europe, last year, for the people who are on the open market, the price went from minus 25 euro per megawatt hour to 125 euro per megawatt hour. Okay? In Toulouse, at the beginning of February, I was paid to make the HPC cluster of Airbus run. Minus 25. So I got a refund of 25 euro per megawatt hour. So that's cool, but when it goes to 120 euro per megawatt hours, which is a standard price in Germany, it starts to be expensive. So the fact is that they are more or less at the same price per core as Amazon, but because they have a very different pricing model when it goes to data and data transfer, then it is very interesting for us, for our users who have a lot of data to manage. So this is one of our partners for the solution I will show you. And we have another partner, which is Uber Cloud. So that slide should be up. So I will just go to, yeah. That was the slide should be up before the Advania slide. Sorry for that. I missed something yesterday. This is our reference architecture. Those are the software systems we are pushing to our cloud partners. And for you to note, there is BGFS here. So we will talk today about Uber Cloud, Simulia, and Panasas, and Advania. But as you can see, we have many others in this ecosystem. And this ecosystem is interesting because we have this cloud management platform that is a multi-tenant cloud management platform. So your workload can go in anywhere. So going back to the Uber Cloud guys, so the Uber Cloud guys, they have nothing to do with taxi drivers or whatever. Okay, they were called Uber Cloud way before. Come back. Okay, there is an auto run somewhere. We did that. You have to get rid of the of a nightmare. I didn't notice there is an auto run. I will try to do it this way. Anyway, so Uber Cloud. Okay, can I? No, I can't talk. Anyway, is it useful? No, that was also on the EMBL slides, and that doesn't bring any information, so we can go in. You will have it. I will give you the slides anyway. The Uber Cloud is a sort of Docker provider. It's a container provider. So it's not Docker, it's Linux containers. I remember that Docker, we use Docker because it's a nice word, but it's just a wrap around Linux containers. Uber Cloud is another wrap. It's proprietary, but it is a multi-tenant container integration, which means that when you deploy your container, always the same container, the container is detecting on which cloud it is, will inherit all the dependencies, and will be able to run. For our industry, one thing we see with the biocontainer is that when you build the biocontainer for the example we made, you bring the database in the container. So that you already see there is some limitation in this model. So you have to bring the link to another container that is on the cloud that is giving access to the data. okay? Which is, I think, what we have in Phenomena. But I'm sorry, I was a bit, it was a bit hard to follow for me yesterday. But this is the model. The containers we are building for the industry are really, really specialized containers. And anything we can reuse, we put that in another container. And Uber Cloud is bringing you this infrastructure. Not for free, of course. So the guys from Uber Cloud, they are very, very nice. And with those guys and with Advania, we built a consortium that you know, that you don't care. Can we stop? Yeah, okay. The Uber Cloud is also giving an interface, a web interface, that gives you a graphic access to your results on the cloud over the network faster than Turbo VNC. One of the key elements of their solution is that they removed all the unnecessary, unwanted ciphering. So if you are already on an HTTPS network, an HTTPS connection, why do you want to do an SSH connection? To launch a Turbo VNC, which is also encrypted inside that. If we remove all those layers of encryption, of encrypting something that is already encrypted, then we can go back to something very efficient. The thing is that you can't crack the first image. The first image arrive encrypted to your laptop. And anytime an image is more than 50% different from the previous one, it arrives encrypted. But all the other frames arrived unencrypted because you only have the changing pixels. So if you don't have the seed or the root image, you can't deduce the next one. Okay? So that there are other codec tricks in there that are all patented, of course. It's again something not open source. So everything goes via a web interface, and you can go to OpenFOAM, Abacus, whatever. Currently, they are really targeting the industry. It's nice. Huh? I don't know who made that. I made so that's the graphics capability. Sorry, it's just DCVN station, DCVN station. And you can share the desktop between two stations. So you can have another guy connecting to your visualization station and seeing exactly the same image as you. So you can share the work and you can do many things. If I wanted to show you the proof of concept we made for Total, one thing that is important here is that we have an NFS storage attached. And the way the NFS storage is attached to a container, that is giving the credentials, so the VLAN configuration and all the credentials to access the data. So the data is on the cloud, it's in the data center, but it's physically attached to your compute nodes. So that's the beauty of the thing. Of course, then you can't do multi-tenant because you will be driven by the location of the data. So they are using that, and it was very successful. So we expect to have more cloud from for Total in the following weeks. Not very interesting, just for you for your reference. And let's go now to the heart of the presentation. So using that ecosystem, we build very annoying. I will no, because I have the animation in. I go back. So yeah. So the Living Earth project was funded by the Food and Drug Association in the US. The idea is to fully simulate a living Earth. So in a living Earth, you have many things to simulate. You have the magnetics or the electrical field of the Earth, which is very important when you want to revive it. Okay, and you have the muscles, and you have the valves, and you have the blood flow. All of that you can measure with scanners and anything. And if you put those information in a simulation, then you can resimulate the art. Okay? So to make it clean, you have to have the guys who are doing the tools. So a scanner now is called an IoT system. It's an Internet of Things. So you have captors. So if you have captors, it's a thing. Okay. So in France we say the Internet of Bidule is the same. So you have to. Those guys have to provide the data to the simulation in the good way. The simulation has to start on the cloud. I wanted to make a live demo, but the current status of the simulation requires 512 cores during 2 hours. So sorry, we can't do that live. So you take a patient and you make the analysis, then you send that to the cloud. And when the simulation is ready, it comes back to the surgeon computers, and the surgeon can then put a stem, for example, on the blood channel. Okay, you put a stem, and then you go back to the simulation and you check that this stem will in fact do what you ask for, which means increasing the blood flow and not making a 0 point somewhere. The main reason where someone is operated and you have to redo it is because the stem is misplaced and you have a counterflow that now then you have the plaquettes are staying and then you have a blood problem. Okay, so that's very important. So that's one of the application. So to succeed in this, of course now it's locked. We had to build I do that, it stays. Yeah. This is the ecosystem we needed to build to make it work. 95 different tenants, 95 different companies working together under the head of Dassault System. Where are the Dassault Systems? They are not only building planes, they are the owners of Simulia, and Simulia is one of the biggest simulation platform or simulation tool. Work. So now one is hard. Yeah, as you can see, you have a simulation of a heart, and this simulation is full. So here you can see the muscle simulations, but we also have the electrical simulations. So anybody knows what's going wrong there on this heart? I do not have the English word for that. In French, we say a flow, or like if the blood was breathing. Okay, because as you can see, this valve is not closing completely there. Okay, so this is a disease. This is what we have to cure, and the surgeon will be able to see that on his computer in the hospital without having an HPC cluster under the floor, because the HPC cluster is on the cloud. To make it a success, we need all those tenants. We need to have something that is constantly billable. We need to have a cloud that is highly available, because of course we need that to work. We need to improve the simulation so it runs in 10 minutes and not 2 hours. And we need something that is, that we can sell to the healthcare programs so that they know what they pay for. Okay, and then we need a visualization system that allows any surgeon in any hospital around the world to see the results on his desktop. And that is the Living Earth project. So today, the only thing that doesn't work are two things to do. One is to improve the simulation, less than 2 hours. The other one is to build all the possible mechanical cues that are existing for the heart disease, and having that in a simple tool, because today you have access to a Simulia interface, and which is a CAD interface. So if you know how to build a car or a plane, it's okay, but when you are a biologist, it's not that not that easy to use. Yeah, one other thing. This is a very important trend in our industry today. We have this joke when we are talking to the guys in the biological, medical healthcare. We said, okay, you know, in the plane industry, at Airbus or Boeing, that's now many years we stopped testing plane by just throwing them from a mountain and checking how many people are alive when it arrives on the ground. Okay, but in the medical area, simulation is not used that much. People are testing the cues on animals, then on humans, and they are checking what's going on. And the next generation of simulation, and I understand it's a bit harder to simulate than a plane, but is to simulate a body, to simulate the cells, to simulate all the body behavior, so we can even test molecules. The current status of the Living Earth project, you can only test mechanical cues, but the idea is also to test molecules on the heart, see what will happen. And that requires a simulation at the cell level. That will be very nice. I want to see the algorithm. So you have to use fractal algorithm to build the muscle, and then you have to bond the muscles together and so on. So that will be very, very interesting. And don't say it's impossible, because what you do today in sequencing, in 1992 it was impossible. So sequencing one 10,000 pair of bars in a minute with a Simulia, with a Illumina system or with a Minion was just a dream 20 years ago. Yeah, because there was so many slides that were passing too fast. I'm a bit ahead of schedule, but I think it's okay. So that's is happening on the cloud, on the industry today, in the life science, and that's what I wanted to show you. So I'm now open to questions. Thank you.